Hi all, this is a video about transformations, and to get started I just want to make sure everyone knows what the transformations are. So I'm going to give them all to you at once, and then we will look at lots of examples of actually applying them. So the idea with transformations is if you know what the graph of some function f of x looks like, we should be able to do fairly simple things like add, subtract, multiply, divide, either the input or the output by some number, and we should be able to say exactly what that will do to either the x or the y values of the graph. So the transformations that we want to look at, again, the idea would be that there's some function f whose graph I already know or have already been given, and we can pick that graph up and we can shift it left, right, up, down. We can stretch it out vertically or horizontally, so we can make it taller or wider. We can compress it vertically or horizontally, so make it shorter or skinnier. We can also flip it either over the x-axis or the y-axis. So you've got your complete list here, and this is what you want to be looking for. If you are adding c to your output, so this is take your y values and add c, your graph is either going to shift up or down. If c is positive, then you're going to shift up. If c is negative, you're going to shift down. So if you see f of x plus 7, that graph of function f should be shifted up by 7. If you see f of x minus 5, then we would shift the graph of f down 5. If you add something to your input, that will give you a shift left or right, but this one's a little tricky. If you add 4 to your input, I think it's very, very, very tempting to say that should shift the graph to the right 4, but it does not. In fact, most of our horizontal transformations, left, right, horizontal stretch compression, they do the opposite of what it might appear that they do, and there's a really definite reason for this. With transformations, we're trying to build up this really simple idea of if you do something to only your y's, then it only changes the y values on the graph, and if you do something to only your x's, it only changes the x values on the graph. But the truth is, if you mess with your input, it's going to change your output. So really what we're doing here is saying, okay, if I don't want to change the y coordinate of a point, what do I have to do to compensate for the fact that there's now an x plus 4? And the answer is you actually have to plug in something that is 4 less than what you would have plugged into the original function. So if plugging 1 into the original function got you an output of 3, then to get that same exact output of 3 from this new f of x plus 4 function, we would actually have to plug in negative 3. So if we plugged in negative 3, we would get f of 1, and we know that original f of 1 is 3. So whenever you have these transformations that are affecting your x's, you're going to have to do this whole undo whatever's being done to your x to figure out how to keep the y the same. So this is actually a shift left 4, and if we had f of x minus 6, that would be a shift right 6. And again, this is for the same reason. If you had the 0.13 on function f of x, then in order to get that 3 from this new function f of x minus 6, you'd actually have to plug in a 7. So I'd have to plug in something that's 6 bigger than whatever I used for the original function to get that same y value. So it's actually moving from x equals 1 all the way over to x equals 7. Okay, if we multiply our output by something, so I'm onto the c times f of x's here. you are going to be doing vertical stretch or compression. So this is going to make your graph taller or shorter. If you're multiplying by something bigger than 1, it will make your graph taller. And if you're multiplying something between 0 and 1, it will make your graph shorter. I want to be really clear here that if you're multiplying by a negative number, the negative part of that is a completely separate transformation. That's some sort of flip that's happening. So let's say I'm looking at 3 times f of x. That says multiply all of your y values by 3. So this is going to be vertical stretch by 3. If we're being really careful, we'd say vertical stretch by a factor of 3, but I'm fine with just vertical stretch by 3. So this will triple all of your y values. You want to be really clear that when you're shifting, it picks up absolutely every point on the graph and moves it somewhere. When you're doing vertical stretch, you don't necessarily move all points. Vertical stretch is always stretching away from the x-axis. So points above the x-axis will stretch up, points below the x-axis will stretch down, but points actually sitting on the x-axis will stay put. Okay, so if we wanted this to actually be vertical compression, we'd see something like 1/8 f of x. So that is 1/8 of your y values, and it'll be vertical compression by 1/8. Again, here there can be a little confusion. So if it's better for you, you could say vertical compression by a factor of 1/8. We're going to multiply our y values by 1/8. I have seen books that will say vertical compression by 8, and their thinking is the word compression already implies it's getting smaller, so you should know that compression by 8 means you're dividing all your y values by 8. I prefer for the number and the word to both reflect what's happening. So vertical compression by 1/8, it will be 1/8 of the height. And again, this is toward the x-axis, so points below the axis will get squashed up towards it. Points above the x-axis will get squashed down towards it, and points on the x-axis will not move. Okay, if we multiply our input by something, we're going to get things like f of 2x. Okay, so this is doubling my input, and again, I think if we're just going on a little bit of intuition here, we might think that that's going to make the function twice as wide, but we have the same problem where really what we're trying to say is if we want to keep all of the y coordinates of our points the same, what do we have to do to our x's? And the answer is I now have to plug in something half as big. So if I go back to the same point 1, 3, I know that if I give a 1 to f, it will give me back a 3. But here, whatever I plug in gets doubled before f gets it. So if I plug in a 1, I'm actually going to get f of 2, which is no longer the 3 that I'm looking for. If I plug in a 1/2, I first double it, which makes it a 1. Then I plug it into f. Then I get out the 3. So this is horizontal compression by 1/2. And if we did something like this, and that can be written 2 different ways. Those mean exactly the same thing. X divided by 9 is exactly the same as 1/9 times x. Both of those are horizontal stretch. So we're going to multiply all of our x values by 9 in this one, and we're going to multiply all of our x values by 1/2, or divide them by 2 in this one. Okay, getting towards the bottom of my page. The only 2 left are the flips, and these I think are the easiest generally. So if you have a negative f of x or an f of negative x. Okay, so negative f of x, that's attaching the negative sign to all of your y's. So that will flip your graph over the x-axis. Be careful, it's easy to write this down wrong just because you're not thinking carefully. It flips our y's, but if our y's are going to flip, that will be over the x-axis. So don't say over the y-axis accidentally because you're thinking it changes your y's. If we attach the negative sign to our x's, that's going to switch all of our x values, so that will be flip over the y-axis. Nothing weird or backwards happens with that one. Basically, to get rid of a negative sign, you need a negative sign, so there's no backwards. All right, that's the complete list of transformations, and I'll post some more videos that give some specific examples. Thanks for watching.